counted neutrinos we mentioned in the first phase. Maybe I've read the wrong ones, but I'm sorry.
The only ones which can really directly simulate them are things like evolution, is kind of the general relativistic GR embodied codes. I mean, there you can actually implement them properly, and they sometimes do, but
I mean, they've also found this out by some kind of simulation. I don't know. I mean, it probably wasn't massive, but. Thank you.
Right. The resolution is of course to implement direct star formation. What is instead done is to use mechanical Schmidt law, where once we achieve a certain threshold we can resolve, we apply this law, which tells us that the current density of the star formation rate is proportional to the current density of the gas to some empirical exponent m. This entire law is totally empirical, so there is no physical derivation from it. And this n and all the prefactors have to be determined from observations. And these days, one is kind of certain that this exponent lies in the range between 1.2 and 1.5. Newly created star particles are in fact not single stars, but they simulate one co-evolving stellar population, which may take up to some 10 to the 5 solar masses per particle. Modern simulations are able to keep track of mass returns and metal enrichment due to stellar evolution over time, which is quite a nice feature. For example, by supernovae or AGB stars, which are stars which are about to die. And stellar feedback in cold gas has to be tuned manually to prevent excessive heating. This is a common problem. Excessive cooling, I'm sorry. This is really a problem in simulations which has not been resolved up to this day. It's difficult to either have realistic feedback or to prevent this overcooling. And what one usually does is to give up the realistic model and just make it work. Then the other part we have to include as black hole growth. And as I told you earlier, the origin of supermassive black holes in galaxies is not yet fully understood. There are multiple theories, but cosmological simulations usually do not touch on them. What is done instead is that black hole seeds are planted into diameter halos once they transfer in 10 to the 10 and 10 to the 11 solar masses. And then these seeds grow according to the Bondi accretion law, which tells us that the growth rate is proportional to the gas density divided by the sound speed of the surrounding gas squared plus the relative velocity of the black hole relative to the gas squared to the power of 3/2. And it's capped by the upper limit by the Eddington rate, which is the maximal rate at which the black holes can stably accrete mass. Sorry? Yes. Spherically stably accrete mass.
Yeah, it's important because it does not take into account that accretion rates or velocities that are shrunk through accretion disks much higher than that.
Yeah, accretion disk accretion law resolved. And this is also one more shortcoming of these simulations because it assumes that the gas has no angular momentum, and this is frankly not true.
Can you confirm how much?
Yes. Black hole mergers can occur during galaxy mergers, and what is done is one skips the general relativistic part and just assumes once they come close enough that they merge into one with the total mass percent. Next, we have AGN feedback from these black holes. This is the entire reason why we need black holes in the first place in these simulations. AGN are active galactic nuclei, which stands for supermassive black holes in the center of galaxy, which are effectively accreting mass and therefore also emitting energy. And this is important for regulating, on the one hand, the growth, and on the other hand, star formation, massive halos at least. Most simulations employ two different AGN modes, which is a quasar mode at which the black holes grow efficiently, and on the other hand, radial mode, where we expect the production of jets and have efficient heating, efficient emission of energy from the accretion. But these jets cannot be resolved, so we just assume that they should be invincible. Okay, next, I would like to present to you some more feedback processes which do not cover the first two I mentioned to you, which are can be classified in general as preventive and ejective. I think it's rather clear what they mean, but preventive means that we prevent gas from falling onto halos. Ejective means that we prevent gas, or do not prevent, we eject existing gas within the halo from the halo. Preventive feedback is dominant in small galaxies and very massive galaxies where we have AGN. Ejective feedback is dominant in mid-range galaxies where we have active star formation. One of kind of this preventive feedback, which is not caused by black holes, is the so-called square chain photoionization, where we have a pool of photons with energies which are about 10 to the 4 Kelvin, and these presence of these photons prevents gas from falling onto halos and equilibrium, because they have similar virial temperatures, and these photons heat up the gas that wants to fall onto the halo, and therefore they prevent these halos from growing. And this primarily affects small halos which have a similar virial temperature. More massive halos are only affected by accretion of these smaller halos. So as I mentioned before, AGN and supernovae regulate star formation and cause the interaction with interstellar medium. And AGB stars, which I explained earlier, and neutron star mergers are also traced empirically, and they enrich their environment with metals and also transfer energy, and they are also modeled in star particles in real time. What we have to achieve in these simulations is to reduce the star to gas to star formation rate down to 1% per freefall time, which is an empirical limit. But as I told you, cold interstellar medium is very prone in simulations to be overcooled, so we have excessive heating, excessive star formation. And what we do is we can either stop cooling for a certain amount of time, we can replace continuous heating, so everything is heated the same and cooled the same, by a stochastic process where some particles are heated more, others are not affected, and the total temperature of these certain particles is higher in the end. And lastly, we can include wind particles which do not interact hydrodynamically, so they effectively take out this energy from gas clouds. I mentioned earlier that we, strictly speaking, should include magnetohydrodynamics, where we have magnetic fields. We know that they exist in galaxies. We do not know how exactly they occur, or how they become the size that they have today from the beginning. So they are artificially seeded like black hole particles in the beginning, and later on they interact with their surrounding barriers and grow in size, grow in strength. On small scales they are important, on large scales, so galaxies and beyond, they are negligible. Then two more things that we can do is to include cosmic rays by further modifying the magnetohydrodynamic equations. And lastly, we can also include radiation hydrodynamics and dust, which is like larger molecules which usually contribute to cooling, but they also usually created once metallicity is high enough, and they also have been only recently considered in cosmological simulations. Okay, now I'm going to showcase two more simulations, and then we will be done because I skipped the zoom-in part. First of all, we have illustrious TNG. It's the TNG stands for the next generation. It's the successor to the illustrious simulation. And it consists of 3 flagship simulations with 3 different sizes, up to 300 co-meter megaparsecs, again from a redshift of 127 down to redshift 0. And we achieve a much better resolution with TNG 50 than TNG 300. And the reason why we have, there exist these 3 different simulations is that TNG 300 displays galaxy clustering well, so large scale structure growth, and also it enables the search for rare galactic objects. While on the other hand, TNG 50 is for galaxy structuring, and structures in and around single galaxies very useful. TNG 100 is kind of the bridge between the two and a compromise between high accuracy and a larger model.
Sorry, how do the initial conditions of these three simulations relate to each other? I mean, is the small box implementing the same conditions, or is it different?
Yes. I think so, but the model is exactly the same. Like all the baryonic models, the hyperdynamic models, all work the same. But I don't think that it's a specific part that's differently simulated.
So you can't compare boxes in
Apart from the size, the elastic TNG also stands out because it does not implement either of these simulation hydrodynamic models, but instead uses the record code which stands between these two models in the flowing mesh. This is a nice picture. Again, we have the filaments. This is from illustrious TNG 300 run. Now the colors are inverted, so bright colors stand for low density, and the greenish color traces the temperature of the gas. So hot and dense regions are again clustered, and we have again filaments. Talking about the power spectrum, as a reminder, this is from the Planck collaboration. The power spectrum, you can see this characteristic shape, and here the dotted lines the nonlinear power spectrum as we expected. This is relevant because simulations usually do not track the linear spectrum, but instead consider the full nonlinear spectrum. And this is the corresponding result from illustrious TNG. So you can see the normal power spectrum for different kinds of matter. The most interesting one for us is the black line, which is one here. The dashed line again stands for the limit beyond which corresponding short noise becomes relevant, so we cannot trust the results beyond this respective line. And again, the limit of the scale is the scale considered smaller than for Planck, just because the volume is smaller. But you can see it rather nicely reduplicates the nonlinear power spectrum as we expected from Planck. Next, the second one I would like to present to you is EAGLE. EAGLE stands for Evolution and Assembly of Galaxies and Their Environments. It's a rather liberal acronym. And here we use smooth particle hyperdynamics, as I introduced it earlier,